So chapter 6, the last section talks about a special type of differential equation that would have what we call regular singular points. We define regular points, and first we defined ordinary points, and those are the points that we had series around back in 6.2. And then in this section we tried to dive into something a little bit more complicated. That's singular points, and we define singular points to be points where if you write your differential equation in standard form, you would get an undefined value at that point for your P and Q functions, and we'll call it capital P and capital Q functions. That's a singular point. Now, a singular point is hard to deal with, but it turns out that if we have a regular singular point, we have ways to deal with that. And for a regular singular point, that's defined by multiplying your capital P function by x minus the singular point, and then getting something that's analytic. And so I had this as an example of a regular singular point. And if you multiply your capital P by x minus x naught, and it's still not analytic, which means it still would have a 0 in the denominator, then that is an irregular singular point. And at this point, for the rest of the class, we won't have anything to do with that because we're not going to be able to solve it using power series. Okay, so so we can only deal with regular singular points. Here's an example. Most of the homework problems that you guys have deal with regular singular points as a definition and how to define it, and then it even talks about finding the indicial equation, which we'll talk about here. But you only have one, maybe two, where you actually have to go through the process of trying to solve for it. And I think the example that we saw is similar to the example that we did in class, or your homework problem is going to be similar to what we did in class. So if you follow through that example, then you're probably going to be able to get the correct answer in the homework. So Frobenius' theorem says that we have a chance of solving for that differential equation if we find these values of r, which we would get from the indicial equation. And so that value of r is given by solving for this equation. And once you find that value of r, you can write your equation in this form. Now, this form is not really that helpful for us because this form kind of depends on what r is equal to. And so we're going to find out how to break that up into different scenarios of r, whatever r might equal to. So how do you find r? Well, that little p and little q that we defined earlier can be written as a power series. A lot of times these things are just polynomials, so we'll just look at them as polynomials, but we're going to be concerned about the constant functions. So if we write out the polynomial series, or the polynomial for little p, and also write it out for little q, then that constant, those two constant terms for little p and little q will be your a naught and your b naught. And if you write your a naught and your b naught in your indicial equation, then this is going to be the function, or the second degree quadratic polynomial that we're going to try to solve for. Okay. So when we do this, we're going to solve for this quadratic equation, and you could probably, if you try to work it out and do some, what's that called, quadratic formula with this, you might see something interesting. And we didn't do this last time, but let's see if we could do it now. Can I write? No. So if we take a look at this initial equation and we write out r squared minus r plus a naught r plus b naught is equal to 0. Oops, let's say a naught minus 1 r. And then we do the quadratic equation, so negative b plus or minus the square root of b squared plus 4a and c over 2a. So we're gonna be concerned about when when the thing under the square root is positive, negative, or equal to 0. And if we look at the thing under the square root, a naught minus 1 squared minus 4 b naught, or a squared minus 2a plus 1 minus 4 b naught. I was trying to figure out when this might be negative, and because we don't have a case for when we broke this down into cases, we didn't have a case where this thing was going to be negative or we're going to have imaginary numbers. So apparently this thing is not going to happen for us, or at least in this class, because we don't have a way to solve for that. So instead of the regular three cases that we usually see for quadratic equations, where you get two distinct real roots, one real root that's repeated, or two complex conjugates, instead of dealing with three cases like that, we have a different set of three cases to deal with, and we kind of eliminate the idea of getting a complex set of numbers for your solution. So the three cases that they present are yeah, we're not going to deal with an imaginary part. Or just we won't be doing imaginary parts. So the three cases that we're going to run into would be the possibility that they're the same, or the possibility that they're different, but the possibility that they're different will be broken down to two different parts. And that first part is that they're different, and if you take the difference between them, you're not going to get an integer. So I think this is a case that this is a case where we had the example and we were working on this. And it turns out that if that is going to be your case, then you're going to have two different linearly independent solutions, and they're going to come in one of these two forms. So they're going to come in c sub n x to the n plus r1, whatever that r root that we found, and then b sub n x to the n plus r2, whatever that r2 that we found was. If they're the same and their difference is 1, then your second function, this case is a little bit easier, I think. Well, maybe not. Your second function, your y sub 2, is going to be a linear combination of y sub 1 times ln x, and then another function that we have to solve for. So case 3 is the one that comes up, I think, a little bit more often, and if they're equal, then there exist two linearly independent solutions of this form. So we tried to do one that fell into case 1, and we didn't quite finish it. And so we can start from the beginning and see if we can walk through that whole solution. So this is the example that we started with. And then we continued on to the next page. And we're starting to get a pattern for that, but let's just go off and take a look at it from the beginning. So here's our differential equation. We have a 3y double prime plus 1/2 y prime plus y is equal to 0. Now, if we write this in standard form, we get the coefficient of y double prime to equal 1 in standard form. Then we've defined your capital P and your capital Q functions. So once you define your capital P and capital Q functions, we're going to multiply the capital P by x minus 0, because we're assuming that 0 is the point that we're looking at. And we'll multiply the capital Q by x squared. And when we do that, we're going to get a constant function. That's too big. Here's my eraser. So we're going to multiply this is called PDF annotator. We're gonna get 1/6, and just for the sake of trying to identify your A naught and B naught later on, you can imagine that this is actually 1/6 plus 0x plus 0x squared and all that, and so we can identify our A naught. And then when you multiply the capital Q of x by x squared, remember to get the little q, we're going to get 1/3 times x. And so if you write that out as a series, we have 0 constant term, 1/3 x is your linear term, and then zeros for everything else. And so remember that you're looking for the constant term. And the constant term in this case is 0. So once you write it in standard form, you can identify your P and Q functions. And once you identify your P and Q functions, capital and lowercase, you can identify your first terms of the P and Q functions. By the first terms, I mean the constant term. And then you're going to get, you're going to be able to write your indicial equation. So now, your indicial equation is r times r minus 1 plus a naught, whatever a naught was, times r plus b naught, whatever b naught was. And then if you put those values in, we're going to get the roots 0 and 5/6. So if you look at these two roots, they are distinct roots. They're not repeating roots, certainly not complex. And if you subtract them, the difference is not equal to 1, or the difference is not an integer. So it's not like 2 and 5. It's not like 5, 6, and trying to think of another number that's difference by an integer. 5, 6, and negative 1/6. Did I do that right? If you subtract them, the difference is 1. Yeah, negative 1/6. Or 11/6 or 17/6, right? 5, 6, and 17/6 would have a difference of 2, which is an integer, in which case we would use the second case. So we have case 1 here. We have 2 distinct roots, and the difference between the roots are not is not an integer. So we're going to create 2 series according to our cases. According to our 3 cases here, we're in case 1. We're going to create 2 series. One of them where r is used, the first r is used as n plus r1 power, and then the second r is going to be used as n plus r2 power. And more specifically, we have a regular power series that we've been dealing with, c sub n x to the n. And then the other one's going to be slightly more complicated. C sub n actually should probably be b sub n, but b sub n x raised to the n plus 5/6, the second root that we found. N plus 0, right. So these are the two series that we're going to look for, and, as if one wasn't hard enough. I'm going to look for two. And then the second one is even more complicated because it has that extra plus 5/6. So the first one, find y sub 1. We're going to approach it like we've been approaching it before. We're going to look at it as a regular function, find its derivatives, as many derivatives as we need to put into the differential equation. And then we're going to replace our original differential equation with the series, and then distribute things, manipulate things so that we have the same powers and same indices and combine them. All right, so here's what happens. Y double prime is the usual y double prime that we've seen in section 6.2, and that's going to be 3x times y double prime plus 1/2 times y prime. Y prime is, again, something that we've seen before, and then the original function y. So we got 3x times y double prime plus 1/2 times y prime plus y. And now let's take this 3x and put it in. So we have the 3, and then the x gets multiplied with x minus x to the n minus 2 becomes x to the n plus n minus 1. There's a 1/2 that goes in here, but the x itself doesn't change. And then the last term doesn't change either. So from here, what do we have? We have n minus 1, n minus 1, and n. So we want them to be all the same. So let's change, let's leave this one alone. So let's change everything to make it look like n x to the n, or x to the k. So what we did here was we're going to let k equal to n minus 1. So we're essentially taking our n, we're adding 1 to each of these n terms. So this will be k plus 1 minus 1. It's just going to be k. This is going to be k minus 1. This is going to be k minus 1. And then now you also change your index starting point. Since you added 1 to every n in here, you're going to subtract 1 to this thing. Oh, this should be n. And then we'll do the same over here. Well, the same substitution. K equals n minus 1, or n is equal to k plus 1. And then we add 1 to all the n's in here, and we're going to subtract 1 from the starting index. So instead of starting from 2, we're going to start with 1. Is that cool? You're not lost already yet, are you? Hope not. There'll be plenty of time to get lost in the next page. So now that we have the same powers, we need to deal with the indices, and we have 2 of them to start with 0 and 1 of them to start with 1. So if we make everything start with 1, that would be ideal, which means we have to take out the k is equal to 0 from the second series, and take out the k is equal to 0 from the last series. And then now everything should start with 1. It should be a 1. Try to remember where those typos are so I can fix that. So now we combine these constant terms, and then everything else from the linear on will be combined into the series. So we have a 3k plus 1 k, c to the k, c sub k plus 1. We have another c sub k plus 1, that's a 1/2 k plus 1. And then this one is just c sub k by itself. And so that's generally what you want to do when you want to write out your one series. When you combine it, write it into one series. You want to also factor these things out because you're going to be solving for one of the C sub k's here. All right. So the relationship is that C sub 1 is equal to -2 times C sub 0. By setting this equal to 0, we bring the C sub 0 on the other side, it becomes a negative, and we multiply by 2. Yeah, right. Oh, because the original differential equation had 0. So if it's equal to 0, then each term of the polynomial would be equal to 0. Does that answer your question? It's a homogeneous differential equation, so it's set equal to 0. Yeah. Uh, I don't know if we're going to be able to deal with non-homogeneous with series. So all the series examples we have here are homogeneous, all set equal to 0. So. And if it's non-homogeneous, then we might need to do something else. Or Laplace transforms. And then crack. All right, that's the constant term, and that's the beginning relationship that we have. And notice the difference between this is this C sub k plus 1, C sub k. In the previous ones, when we deal with second order differential equations, we saw C sub k plus 2 and then C sub k. And so we kind of have the odds together and the evens together. But here we notice that all the numbers are going to be following the C sub 0. It's going to be all written in terms of C sub 0. So we know that we're only going to get one solution out of this. And our second solution will come when we change the R1 to R2. So we have our relationship. And then what we could do is this is good for the series. Says it's good for k is equal to 1 all the way off to infinity. And so we could do it one by one. We should do it one by one. We'll let k is equal to 1 to 2, and then hopefully find a pattern that way. So we'll let k is equal to 1. We're going to get 3 times 1 plus 1 times 1 plus 1 half times 1 plus 1. C sub 1 plus 1, that's C sub 2, plus C sub 1 is going to equal to 0. So I got this simplified, and then I solve for C sub 2. And C sub 2 is equal to something with a C sub 1 in it, but C sub 1 is equal to -2 C sub 2. So now I was able to write the C sub 2 as, or in terms of C sub 0. And then we put 2 in there. We're going to get 3 times 2 plus 1 times 2 plus 1 half, 2 plus 1, C sub 2 plus 1 plus, and then we have C sub 2 here. Set that equal to 0. We're going to get C sub 3 is equal to something with a C sub 2, but we know what C sub 2 is. So we're going to make that replacement for C sub 2 and then eventually get something with the C sub 0. And we could try another one here, but I was done. So this is our series up to 1, 2, 3, 4 non-zero terms. And sometimes when they ask for solutions, they ask for the series up to, 3 or 4 non-zero terms. Yeah. Yes. I'm also trying to remember where my mistakes are. I got indices written incorrectly in a couple of places, but once I fix that, I'll post it. Yeah. Ever, maybe. Yeah, in the homework, no. In the homework, I think there's only 2 problems, and the one that we did was looking for something like this. And a lot of times the series notation is kind of hard to decipher. I mean, you can really just get it from here, but it still gets a little complicated to find a pattern. All right, so that's y1. So that's one series. Now we have to look for the other one. Y2 is a little bit more complicated than what we're used to. Y2 is of the form b sub n x to the n plus 5, 6, our second, it's raised to the n plus our second root from the initial equation. So if that's your y, that's your function, you find its derivatives, and now the derivatives are going to generate these n plus 5, 6, and n plus 5, 6 times n plus 5, 6 minus 1, whatever. But it's just the derivative, right? Derivative of infinite series. You do term by term differentiation. But I want to circle something that's not a typo, and that n is equal to 0 and n is equal to 0. These indices don't change because they still do exist. These n at 0 still would exist for this particular series, even after you've taken the derivative. Okay, and what you could do is I encourage you to go back to our example and the examples that we've been doing in 6.2 and write out maybe the first 5 terms and then take the derivative once and twice, and you'll see that the indices do in fact change for the series. But we did this in class yesterday or last time. We'll see that if you write out this series, the first few terms, and then take the derivative, you'll see that the indices will not change. It's always going to start when n is equal to 0. So that's one important thing to note. All right, now let's drop it into those places where you have the function, the derivative, and the second derivative. So we have 3x times the second derivative plus 1/2 times the first derivative plus the original function. So now let's incorporate the 3x into here. So the 3 comes in, and then here we multiply the x to the n minus 7/6 times x. So we add 1 to the power, we get x to the n minus 1/6. Here we have a 1/2, but the power of x doesn't change, and the last one doesn't change either. So now we have a choice on trying to figure out what we want to line up our x's to be the same power. So there's n minus 6 for 2 of them. So I'm deciding to use n minus 6 over here, which means I want to change this power. So what do we do to change that power? So remember that these powers, when you take derivatives, you're really subtracting 1. So it's about subtracting and adding 1 to these powers. So here it looks like I want to subtract 1. So I want to replace n with k minus 1, or k is going to be equal to n plus 1. So do that switch. You're subtracting 1. You subtract 1 from n. You get n. Instead of n, you got, this should be a b. Another typo. It should be b sub k minus 1 instead of b sub n or b sub k minus 1. And everything else will remain the same, except I changed the n's into k, so everything looks like a k. Note also the change in indices, and we only had to change the index for one of them. Okay. So now that we got that change of index, now all our powers are the same, x to the k minus 1/6. But we have a 0, 0, and a 1 here. Did I just repeat this? There's nothing different here. I just copied it. Copy and paste. That's what I do when I do these problems on a computer. I just highlight, copy, and then paste. And so maybe I copied and pasted. What? Yeah, to go to the next line. All right. So what do we want to do? We want to start our index at 1. And so I want k is equal to 0 business happening here. For the first series, the second series also has a k is equal to 0 term. And then the last series doesn't change because it already has an index at 1. So when I do that, I need to start this at 1. Another typo. Should have my typo in a different color. Yeah, try to catch it later. Turquoise for typo. I was just thinking a highlighter. Is there a highlighter? There's a highlighter. Typo. Where else? Typo. Couple of other typos here. Typo. Typo. Yeah. Yeah. I know. Too bad. All right. Let's combine those constant terms that we took out. Oh, typo. Let's combine the constant terms that we took out, and then I didn't really combine them yet. I kind of just grouped them up or rearranged it so that these two can be together. Well, it took several steps here. And now let's combine the series terms together. And remember, the way to combine them is they all should have the same x to the power. So the same x to the power gets taken out. And now you have to look for where they have the different b sub something. So here they have the same b sub something that gets combined together with the b sub something. And then this b sub k minus 1 is the other term. All right. And there was something funny that happened here also yesterday that we've kind of noted. This first term, or this term that wasn't involved in a series, if we factor out an b sub 0 times x to the negative 1/6, we're going to get 5 over 12 negative 5 over 12 plus 5 over 12, which says that this is equal to 0 regardless of what b sub 0 is equal to. And remember, one of the points that they made in the cases is that b sub 0 cannot equal to 0. So that, in effect, will be our arbitrary variable. So we're going to let b sub 0 be just b sub 0. It's almost like a C2 or something like that when we used to write them as C1 y1 plus C2 y2. So this is your arbitrary constant that we're going to come up with. Now, for the rest of them, k goes from 1 to infinity. We're going to try to find the recursive relationship. And here we can solve for b sub k as something with a b sub k minus 1. And if we do that, we'll start with k is equal to 1. We get b sub 1 is equal to something with a b sub 0 in it. And remember, b sub 0 is some arbitrary constant. And then we let k equal to 2. Oops, this is the k is equal to 1. K is equal to 2. We get something with a b sub 1, but we'll replace that with b sub 0. And then k is equal to 3. Um, yeah, so the leading term here, so b naught, all we can say about b naught is that it's not equal to 0. Are we looking here? Oh, yeah, yeah, I factored out a b naught. Yeah, because that's how the series was. The series looks like this. And so, oh no, the first term is b naught. Actually, oh, that's another typo. That would be a big typo. So this should be b naught x to the 5/6, and b naught times, what's x to the 5/6 plus 1? 5, 11/6, 17/6, 23. So yeah, so that's not equal to 1. Thanks for catching that. Our series should be b naught or bn x to the n plus 5/6, where n goes from 0 to infinity. So the first term would be b sub 0, x to the 0 plus 5/6. So our first term should have an x to the 5/6 in it. So it's not equal to 0. Okay. But they all have a b naught, and that's what we took out. So we took out a b naught. Yeah, so we take out a c naught, since they're all going to have these arbitrary constants. Each c sub something is always going to have a c naught in it, and each b sub something is always going to have a b naught in it. That's how the recursive relationship was working. They all have b naughts. All right. So according to, or here they even took out a 5/6. So according to the homework, it would be c naught times 1 plus whatever the pattern was. And here they have c naught, c instead, well, we use b naught. Here they have c2, and then they took out an x to the 5/6. You can imagine each of these having an x to the 5/6, multiplied through with the power. So this is how they would do it. All right. Whew, any questions? So I'll post this file, or the nice, neat, without any marks file after I made the corrections. I'll just post this one with all the sloppy corrections and arrows and underlines and stuff. Okay. All right. Any questions? Yeah. So for the y1 term, that would be back in, yeah. So this is C1, and this is C2, and C3. Okay. So the power series, your y1 should equal to n goes from 0 to infinity, c n x to the n. So that's n plus 0. Uh, the c naught c1 x plus c2 x squared plus c3 x cubed plus dot dot dot. Oops. So this is equal to c naught. We don't know what, c naught is the arbitrary function. And then we have a c1 is equal to minus 2 c naught. That's c1 times x. Yeah, that came from when we split up the series. We got the k is equal to 0 terms, and then that's how we got that. Okay. All right, so this thing goes on, and then you're going to get your the series that you're going to try to match up with the homework. Ooh, yes. So sometimes you need to solve for a differential equation, and you just need to estimate it, approximate it. And in calculus 2, you learned that series was good for approximating functions that are near the point. And so um, if if you're looking at a differential equation and you can't seem, and we don't have any way to solve for this particular differential equation using, we have constant coefficients, that these aren't constant coefficients. This is not a Cauchy-Euler equation. So we don't have another way to solve for this. So we would approximate using power series. And usually when you get to the third order power series, it's usually good enough in most of the applications that you would use in physics and engineering. I'll say engineering. Physics people are still kind of whatever. Anyways, so you only need enough accuracy, and it's usually up to the third degree polynomial. And so having this information for your y1 and then the other piece of information for y2 um, would be good enough in most of the engineering applications that you would use series for. Okay. Any other questions? All right. Is it better? I don't know. Uh, this is for PDF stuff. Uh, hmm. Is it better than OneNote? I'm gonna commit to OneNote for another semester and see if I like it. So the thing about this is PDF, and I don't know how easy it is to insert more space or grow your page or whatever. No, but it's only like 40 bucks. I mean, for a student, 40 bucks is probably not only, but it costs money. All right, let's move on. Next chapter. So 6.4 has some special functions that you may run into And one of the functions that they, in particular, they talk about is the, I forgot what it is. Seems so important. I can't remember. Bessel, Bessel function. And so, uh, so I have some notes on this, and maybe I'll make a video. I think I do have a video on coming up with this special function. Um, but I'm just gonna fly through this real quick. Here, here's a case where you have identical roots. In this case, the roots are equal to 0, which might seem easy, but you're going to have two functions. One of them is going to be the regular function that we would look at like as if it was a regular power series, and then the other one's going to involve an ln and some other function. So if you walk through this particular example, you get y sub 1 is equal to this this seemingly complicated looking series that might not look like it has a pattern, but it actually has a distinct pattern. And this is called the Bessel function of order 0, because apparently there's more Bessel functions. And this is one of those functions that's defined by a series. In other words, they don't have a nice function for it. They define it using a series, and the series is obtained from the differential equation. So this is a graph of the Bessel function. If you look it up, if you type Bessel function in Google it, you'll see. Now to find the second solution, it involves that the second solution will incorporate the first solution, and then we'll have another solution of a different form, starting with n is equal to 1 here. And then there's a corresponding Bessel function, and they call it, instead of calling it j, see how long this is? Yeah. Instead of calling it j, they call it y sub 0. So Bessel functions come in pairs. They come in j sub 0 and y sub 0 and j sub 1 and y sub 1, etc. And then you come up with this thing. So I saw this. This is a problem, actually, a series problem that's in the Calc 2 section of your calculus book. It's in Stewart's, I think, which is the book that you guys used, right? Or you guys use Wiley. In any case, there's Euler's constant that comes from a series from Bessel's function. Anyways. All right, so I'll make a video out of that. Let's begin the next section. Laplace transforms. So what is Laplace transform? Laplace. Let's see if you can let's try to look at differential equations from this point of view. What happened? There we go. This is how I like to introduce Laplace transforms. We're gonna go between two different worlds here. We're gonna go in the real world. We live in the real world, and this is where our real world problem is. It's a differential equation. And so what we would do is we have a differential equation that we're trying to solve. And then in the real world, and what we've been doing all semester, is we're using calculus to get our solution. So use derivatives and integrals and series and stuff like that, all dealing with calculus. So we have our differential equation, and then our solution is y sub t. Laplace, if we think about Laplace, Laplace exists in another world. So what we're going to do is we're going to venture into the Laplace world. Also known as the S world. And what's going to happen is that our difficult looking differential equation in the real world is going to move into the Laplace world and become an algebraic equation. And then, since we have an algebraic equation, we use algebra, which is sometimes easier than calculus. We're going to use algebra to solve for this equation, and we're going to come to our solution. And in general, we denote it as a capital Y instead of the little y in the real world. When we're in the Laplace world, we're going to denote it as a capital Y. And then the variable that we're going to be dealing with is going to be S in the Laplace world versus T in the real world. And so from here, we're going to translate our capital Y of S solution back so that we can be in the real world again. Okay? So we're bypassing some calculus to do some algebra. Now, I have to admit, the algebra that we use is an algebra that you probably didn't see until you got to calculus. Does that make sense? So one of the big deals that you're going to need to know here is partial fractions. Now, I don't know if your calculus teacher told you, but partial fractions is just algebra. There really just wasn't reason to teach you this in algebra because I don't know why. What? In college algebra, yeah, and so appropriately so. Yeah. Well, the thing is that people, algebra teachers probably don't teach this because students say, you know, when am I ever going to use this? Like enough times already. And algebra teachers already have a hard time saying, well, you're going to be able to factor when you're trying to deposit money in the bank. I don't know. When are you ever going to use this? Yeah. So the point is, it's just algebra. Okay. So as much as it might have pained you back in Calc 2, it's all just algebra. There's absolutely no calculus involved in it, except the main use for it is in calculus. So um, that's the algebra. So in going to the Laplace world, we need some sort of transition, and then we do the algebra, and then we need to jump back to the real world, and then we need to do another transition. So that's what we're going to study, is a transition. So the transition that we're going to make is denoted by a fancy L. We're going to take the Laplace transform of a function. I call it little f. So Laplace transform is an operator, and for linear algebra people, it's a linear operator. And what that's going to do is going to transform your real life function into a Laplace function of f. Did I say f or s? Function f of s. And then, of course, you want to be able to go back. So we're going to do an inverse Laplace transform to transform back. And what we would normally transform here would be a solution that we found in S and then make that into the y of t. Now, these are curly brackets to just say my input is a function. I mean, technically you can put parentheses, but people tend to use curly brackets for that. I just want to make it a capital Y. That's how I write capital. This is how I write capital X's and capital Y's. If that's what you need, go for it. All right. Because here we're going to have different functions that we're going to transform, and then we're going to go into here, and then we're going to do the algebra, and then we're going to solve for y of s in our differential equation will turn into an algebraic equation where there's a y of s in there somewhere, and then we're going to solve for the y of s, and then we're going to take our y of s back to the real world, and it's going to become y of t. Okay. Are you guys ready to go to the Laplace world? All right. So this is my big picture. I like this big picture. Yeah. Sometimes. So the first thing we're gonna try to discover or try to find is, what does this Laplace transformation look like? So it says that I'm supposed to be able to take a function and then change it to something with an s in it, a function of t, and change it with something with an s in it. So I need my notes. This is our Laplace transformation. So improper integrals, when are we ever going to use that? One of those things in Calc 2 where you think, oh, improper integrals, when are we ever going to use that? Here we go. Laplace transformation is an improper integral going from 0 to infinity of e to the negative st. Now notice the s and notice the t. and then f of t dt. Notice that the dummy variable here that you're integrating with respect to t. This is an integral with respect to t. E to the negative st is like a function that pushes your f of t down with the hopes of it converging. So, aside from trying to remember your partial fractions, you also have to try to remember your improper integrals. So we're going to approach this with improper integrals. And let's go really simple in the beginning, because what we want to do is we want to figure out where the functions go in the Laplace world. And the easiest function in the real world to look at is a constant function 1. So let's do an example of trying to send our function f of t is equal to 1 to the Laplace world and see how it's going to look like over there. Well, let's just put it into this Laplace transformation. So we would denote it as L of 1. 1 is the function that we're putting in. And this is going to be an integral from 0 to infinity of e to the minus st times 1 dt. So s is a constant in this integral. In this integral, s is a constant. T is your integrating variable. You're integrating with respect to t. So s is a constant. The integral of a constant times t, e to the constant times t is what? 1 over negative s or something? Oh, with the improper integral rules, limit as b goes off to infinity of integral from 0 to b e to the minus st dt. And that's going to equal to limit as b approaches infinity of 1 over negative s e to the negative st. Is that right? You do a u substitution. Let's make sure. U equals negative st, du equals negative s dt, dt equals 1 over negative s du, right? Well, however you want to do your substitution. Remember, s is a constant in this integral. Okay. So we're going to evaluate this when t goes from 0 to infinity or to b, and then take the limit. So it looks like we put b first. B goes off to infinity of 1 over negative s e to the minus sb, and then minus, and then we put 0 in there. It's just going to be negative s, 1 over negative s. E to the 0 is 1, I think. Yeah. So you let b go off to infinity, then this expression here will get closer and closer to 0, right? So that's going to just disappear. What do we have left? 1 over s. We did it. We Laplaced our first function. So the Laplace transform of the function 1 is equal to 1 over s. Yay. Cool. This would be our f of s. So f of t, if we're going to make a table, capital F of s. So we got 1 here and 1 over s here. Yeah. Yeah. The Dirac delta function is a special function that's used especially for Laplace. Alan?
Here's a problem that takes 10 pages in an hour and is awful. And now that you've done that, here's a way to do that exact same problem every time in 2 seconds. Is this going to make all the crap we've done, I'm sorry, all the stuff we've done up until now?
No.
No?
No. It's going to be.
It's not that miraculous?
No. So it's not that miraculous because we're still going to get tripped up right here. The partial fractions and then the sending this back. There's still going to be some tripping. So, all right, that's our preview. I'm probably going to do a video on sections 7.1 and maybe a little bit of 7.2 over the weekend. Have you responsible for it and do one of those flipped classrooms again. Oh, exams.